Good morning, everyone. Welcome to our second webinar in a series of 4 webinars, this on the science of forest carbon management. I'm Charlie Levesque. I'm the Executive Director of the Northeast State Foresters Association, under which the Securing Northeast Forest Carbon Program sits. It is funded by the USDA Forest Service Landscapes Scale Restoration Program grant program. So we want to thank the USDA Forest Service. As you may know, we have a website for the whole effort under northeastforestcarbon.org. We encourage you to go there. All the materials for the program are there, including recordings from these webinars. Also there are the state lead contacts. Each of the states in the program, which are New York and New England, the 7-state region, has a state lead contact for forest carbon, and those are all listed there with contact information. Reminder, if you are a forester, you get SAF, CFE credits for watching this webinar, but you got to stay on for the whole webinar. We're given a report and we know how much time you've stayed on the webinar. So I encourage you to stay on for the whole thing to get your credits, and you'll get your credits automatically if you stayed on the program. So this webinar and all in the series of 4 that we've got going on this month are being recorded, and they will be made available shortly after the webinar. The one from last week is up along with a PowerPoint presentation. We'll do the same for this one, so you'll be able to see it at a later time or send the link on to others to watch. A little bit on the webinar tech associated with this webinar. We have over 500 people registered for this webinar. And so it's no telling how many will be on, but ultimately that's a lot of folks for a webinar. And so obviously you are all muted and you have no video access because of the numbers. We are going to be using chat for any questions that you would have. And I would encourage you to use the chat carefully and judiciously. Have had a number of complaints from last time that extraneous chat was going on and it was distracting, because remember, when you put something in the chat, it can pop up on the screen. It's distracting to the presentation. If you have a question, please do ask it. We're going to get to those in the end. But again, just be careful about how you're using the chat. At the end of the presentation, we will be answering as many questions as we can that are put in the chat. If your question is not answered, and it's very likely that not all of them will be answered with the kind of numbers we're talking about, we will attempt to answer any questions that you send me directly by email. My email address is on the screen, levesque@inrsllc.com. And so I encourage you to send questions that don't get answered that you want answered to me afterwards. We had some of that after the first webinar last week. And remember, when you're posting questions, if you want everyone to see them, you got to make sure that the chat function is set to send to everyone, not just the host and the panelists. That's up to you, obviously, but that's how it works. And there is a raise hand function, and we are not using that. We can't possibly do it with the numbers that are on the website, or rather the webinar. And so please don't use the raise hand function, but do use the chat judiciously. So we're ready to begin. And at this point in time, I'm going to introduce our presenter, who also presented last week and will present next week as well, Dr. Alexandra Kosiba. Ali is the climate forester for the state of Vermont. And so Ali, go ahead and bring up your PowerPoint, and then we'll turn off our video so they get the full screen.
Great, thanks, Charlie, and welcome everyone. Yep, and like Charlie said, I am going to stop my video. And that looks good, Charlie?
It does, it's perfect.
Great.
Go ahead.
Okay, great. All right, so as Charlie said, we're talking about the science of forest carbon management today. And this builds off a lot of what I talked about last week, the science of forest carbon. So what we're going to talk about today, key concepts of forest carbon management. I'll go into carbon management strategies, and that will be the sort of the bulk of what I'll talk about today, different ways that we can think about and manage our woods with carbon in mind. I'll share some resources that we have out there, and that's a developing field, of course. We're always getting new resources for landowners and foresters. And I'll talk about some field methods and tools we can use to assess carbon. I'll end with some cost benefits analysis as done, the state of Maine is working on, which is interesting to show carbon benefits and costs of some of these practices. I'll talk about some trade-offs and considerations that we should consider when thinking about carbon in our woods. Follow up with some wrap-up take-home points, and we will have time for questions and answer. And this, just a reminder, is really focusing on the New York, New England region, but a lot of what I talk about here is applicable to other forest types and areas. So just to step back, it's important for us to consider that all land use decisions, all decisions or lack of decisions impact forest carbon. So one way to think about this in this top schematic, which I really like, although it's abstract, is this idea that we, when we're thinking about forest carbon, we want to minimize emissions to the atmosphere. So we don't want to emit more, or we want to sort of reduce the amount we're emitting, and we want to maximize carbon stocks. But we have to remember we have other things to consider with our forest ecosystem, right? So we have land use conversion from forest to non-forest conditions. And sometimes that's a necessary need for housing or agriculture. And so balancing that. We also have resources that we use. So can we use bioenergy or biofuels in replace of fossil fuels? Wood products in replace of other products that we use like concrete or steel. And so you can see that there's sort of a balance here and some trade-offs that we need to consider when we're talking about forest carbon. And I introduced this last week, but this concept of the difference between storage, carbon storage, and flux or sequestration, where flux again is a combination of emissions to the atmosphere, which happen naturally through decomposition, combustion, fire, and just natural metabolism of living organisms. And then sequestration, which is the taking in of carbon dioxide and storing it. And you can see that if we are favoring carbon storage or sequestration, we might have different goals for our forest system. And leaving forests to accrue in age here on the left-hand side, carbon storage, will then mean less sequestration and vice versa. So it's just something to consider. And this is why when we talk about carbon, we want to talk about scale too, right? So the idea that we do a lot of different things in the woods and it sort of balances out to maximize both storage and sequestration. When we're talking about forest carbon, we really have the ability to alter or consider the above ground live biomass pool, which then affects the below ground live biomass pool. It may affect, we can maybe affect the deadwood pool through forestry practices. I'll talk about things we can do there. And certainly harvested wood products, what we harvest from the woods, the products that are made, the waste or the efficiency of those products can really dictate how much carbon gets stored in those harvested wood products. But we have as I illustrated last week, the litter and soil pools we don't have a lot of control in increasing them. What we should focus on more is stabilizing them and not impacting them. When we think about forest carbon management, there's a lot of different ways we can think about this, and it's quite complex because first of all, we have two types of carbon benefits. The first is emissions reduction. So these are actions that we can use to keep carbon out of the atmosphere. An example of that is a forest parcel potentially that is slated for development and it gets conserved and maintained as forest. So the emissions that would have happened from that land use change are stopped. The other way we can have a carbon benefit is increase the rate of sequestration, so the sequestration and the carbon storage in that forest or in harvested wood products. So that's taking more carbon out of the atmosphere. And you can see that those two actions actually have a different effect on the atmosphere, right? So the top one is not increasing the amount of carbon dioxide in our atmosphere more, and the bottom action is actually lessening that amount. So they have different results. Both are really great actions to take, but but you can see that they will have different outcomes. And this really does play into next week when we talk about carbon offsets and carbon payment programs. There are also different timings of the benefits and the timings of the cost. So benefits, we can have a delayed benefit, immediate or sustained over time, and same with costs, right? So example of the emissions reduction, conserving land that may be slated for development, that's an immediate carbon benefit here and an upfront cost, right? So the cost of conserving land will be usually quite significant. An example of increasing sequestration, carbon storage, things like tree planting, right? So that again is going to be an immediate cost. You need to pay for those trees and those seedlings and putting them in the ground. But the timing, that's an upfront cost here, but a delayed carbon benefit, because those trees as seedlings or saplings will take a few decades to really start growing, sequestering and storing carbon in large amounts. So it has an upfront cost, but a delayed benefit. When we talk about a lot of the practices I'll go into in this talk about silvicultural practices we can use in the woods, we can usually combine emissions reductions and increasing carbon sequestration and storage. And we hope to have both sustained benefit and ongoing costs, right? That's sort of the sweet spot that we can get to in forest management with the tending of our forests and good forest stewardship. So the key concepts is that we can, that timing will vary. We can increase or decrease or sustain the carbon pool or alter the rate of change. And the ideal scenario across a parcel is we use multiple strategies to achieve that and across the landscape. And the key part of carbon management is that we have to align carbon management with objectives of the site, conditions of the site, forest type, vulnerabilities, but also the landowner's risk tolerance. So considering the trade-offs and benefits of some of these practices is really important. And key is that nothing is guaranteed. When we talk about natural disturbances, climate change, those will affect carbon balance in forests in somewhat unpredictable ways. And so keeping that in mind is critical. And again, I brought this up last week, but just to reiterate the importance of resilient forest carbon, or sometimes called durable forest carbon, then this is the idea that management for forest carbon really needs and has to include considerations for forest resilience in the long term and adaptations to climate change. So we have to ensure that carbon is not only sequestered and stored now, but into the future, right? If it's going to be immediately released in the near term, that's not resilient forest carbon. And we could see, that climate change could bring changes to our species composition, disturbance rates, insect and disease dynamics are really one of the wild cards that we don't know what's coming down the pike. And to do this, and I'm not going to get into this in detail here, it's another talk about resilience and adaptation in our forest management, but it's key to evaluate the stand's vulnerabilities to climate change, to insects, disease, disturbance, natural disturbance events, and then using management techniques to try to address or reduce those vulnerabilities. And key here is monitoring, evaluating the outcomes, adjusting strategies based on those outcomes. And some examples here from our state here in Vermont, and this is true across the region, of things like old logging roads that are causing significant erosion on our slope. That's loss of carbon that's happening. Without controlling and mitigating that impact, we're losing carbon from our soil. As you remember from last week, soil carbon is the bulk, more than 50% of the carbon in the forest. And so that's not a resilient system without mitigating those effects. This is an example of spongy moth defoliation. And any 1 year of defoliation by insects won't be a huge carbon detriment to a forest, but multiple years, and then if layered on with other weather events like drought, can cause widespread mortality. So again, a stand that has a lot of the same species, they're vulnerable to the same disturbances or same insects, may not be resilient in the future. There's some great research by Kate Miller looking at regeneration patterns around our region. And she's found that there are many areas where there's not sufficient regeneration to replace the overstory canopy. And that's another example of forest conditions that are not resilient to future change. And this right-hand photo is actually a stock photo from Microsoft. And it's beautiful. I think lots of people would consider that, but I see this as a really not resilient forest. You have very skinny, closely spaced trees of one species, likely planted. They're very vulnerable to wind throw, to an insect outbreak. There's no regeneration in the understory. So while this forest is storing carbon at the moment this photo is taken, it's not resilient forest carbon that will be stored in the long term. And so this stand could use some carbon-friendly forestry to think about maintaining that forest carbon in the long term. So now I'm going to talk about these strategies and different ways we can think about carbon-friendly forestry. So the first and arguably the most important is avoiding forest loss. And this is really critical. It is the biggest loss of forest carbon benefit that we have in our region or in forests in general. Because it's not only do you lose the carbon that's stored in the forest, and some of those trees will go into long-term long-used wood products, durable wood products. But when we have forest conversion, the soil is tilled and stumps are removed, the land will be graded. So you get reductions in not only the live above ground biomass, the below ground biomass that you wouldn't experience in a normal forestry operation. Often dead wood, litter is removed, and you can have losses of soil carbon with that tilling and that grading of land. And then additional to those losses of the carbon storage, you lose that forest as a sequestration sink in the future. So we call this foregone sequestration. And that means that forest is no longer contributing to sequestration potential anymore. And as that forest, the longer that land is non-forest, the more that foregone sequestration potential accrues. So this practice really keeps carbon in the forest. I'm going to use these little arrows as I showed earlier in the presentation. Remember, so this is reducing emissions. This is really a reduction in emission strategy. Again, there is this additional foregone sequestration potential we get in keeping forests as forests. And of course, there's myriad other benefits of forests that we all know and love, and keeping them intact is critical. There's certainly considerations. This is the costliest practice that we have. Land prices in our region are skyrocketing. I'm sure we all are aware. And often landowners in our region have forest land as a nest egg to have money for their retirement. And so that's a really critical trade-off we will have to consider. We also need we need land for housing and other uses. So there's trade-offs there. And then thinking about the permanence of protection. And that's just sort of a consideration for this strategy. If we look at our states across the region, it's quite varied. So the blue here is total carbon flux when we convert forest land to other uses. And across our states, we all have some of that. And then the green is land that's actually converted from other uses back to forest. And this usually just happens sort of passively, where a field is not used anymore and trees occupy it. And so the net here is the numbers. So for example, Connecticut has net conversion to forests as far as total carbon flux, whereas here in Vermont, we have total carbon flux that is positive. So we're actually emitting more from land use conversion than we are gaining with new forest land. The next on the strategies is establishing reserves. So this is passive management or non-extractive management. And it can occur across multiple scales, importantly. I think people think of this as it has to be the entire parcel. It could be the entire parcel. It can happen across a stand or a group of trees, right? So this is one of those strategies we can actually pair with some of the other strategies I'll talk about in one parcel. and it can be may or may not be permanently conserved, right? So you can do passive management without any permanent conservation. The goal here, again, is emissions reduction. So it's keeping carbon where it is in the forest. You're avoiding emissions from timber harvest. Can promote other ecological benefits. So this is great to promote biodiversity, develop old forest characteristics, build soils, protect unique sites or climate refugia. So these are places that we think might be more buffered from climate change. It's really best on those really unique, rich, protected sites that have a low risk for disturbance. Because in this right-hand figure, see when we have any sort of disturbances that happen in our forests, we have carbon losses. This is because we get mortality, branch breakage, declines in vigor, all sorts of things that will happen from a disturbance event like a windstorm, insect outbreak, drought event that will cause carbon losses that will then recover. So without natural disturbances, we know that if we have a stand that ages, carbon sequestration will naturally decline. And we could have more carbon losses from mortality compared with active management. I'll show you that on a figure in a couple more slides, but we do know that actively managed stands have lower rates of natural mortality because those trees are harvested and taken off site. When you have natural mortality, that is a great way to get carbon into the deadwood pool, but it does mean slow release of carbon emissions over time. And it might not be the best for forests that are in need of restoration, fire, that are dependent on fire, or with forest health issues, significant climate vulnerabilities. And importantly, it can cause leakage, which I mentioned this last week, is when reductions in timber harvest one place are just offset with increases in timber harvest elsewhere. And that can be in the same region, the same state, or it could happen elsewhere. It could mean more imports of timber from elsewhere where we don't know what the forest management practices are. And we do know in both observed studies. So here on the left is a long-term study at the Penobscot Experimental Forest in Maine, where they observe the differences in carbon stocks across these treatments. So this is a sort of retrospective study on actual trees in one location. They did find that the control, the reference, did store more carbon over time than the other treatments. And then we also have results from modeling. So this is sort of the two ways that we have data about carbon. It's either retrospective studies looking at a forest stand over time, or we can model from forest conditions model forward. So they both have pros and cons and assumptions. But we see that this modeling study, this was on a maple beech birch stand in Vermont, using Vermont data. After 160 years, the no management had more carbon storage than the other treatments. So the next strategy is one of extending rotation. So this means increasing the time between harvests to grow larger trees. Recommendations from some carbon sources typically suggest an additional 5 to 15 years. Sort of depends on the forest type, the species, the conditions, the landowner's risk tolerance. So this is a combination strategy. You're avoiding emissions right now by not harvesting, and you're hopefully storing more carbon in those trees as they grow larger. So it also could increase the carbon that goes into long-lived products, right? So if you can get bigger trees, you might have more efficient milling, or those trees might go into different products. Could increase lumber value. Again, this is dependent on a lot of factors. If we pair this with other actions, it can be used to increase stand structure and resilience. So we have areas where we extend rotations and areas where we do some of the other practices I'll mention in the following slides. This is not suitable for all stands. It really is imperative we consider forest health and regeneration status in our using of this practice. And gains can be lost if there's a disturbance. So it does pose a risk for waiting longer. There's just a risk that there could be disturbance on that site, right? So it also does not necessarily advance resilience or adaptation to climate change, and because it doesn't necessarily provide both species and structural benefits. So just leaving the woods and extending those rotations, not doing anything to increase the regeneration component of the forest, the structural complexity of the forest. But again, we can pair this strategy with some of the other strategies I'll mention. There is an opportunity cost that needs to be considered by the landowner. Delaying harvests could alter the economic returns. And again, this could cause leakage, especially if done at large scale. And this sort of gets to next week when we talk about carbon offset markets. There's a number of programs that do pay for delayed harvest, for extending rotations. We do know from research, longer rotations do keep carbon on site, but it can depend on the type of harvest, right? So in this work, this is the same study I showed in the last slide, but some different data. So Maple Beech Birch Forest, looking at the differences between short and longer rotations, single tree selection, shelter wood, and clear cut. And so especially for single tree selection here, and a little bit for shelter wood, you do get more carbon more carbon gains extending that rotation. The clear cut, interestingly, the shorter rotation has considerably more carbon stored in landfill. That's in this dark blue. So it does depend on a lot of factors, forest type, silvicultural practice, and time. We can also use thinning to improve the growth of remaining trees, right? This is sort of standard practice we can consider in our woods. We can use it for carbon, increasing carbon sequestration, right? So this is a goal to increase the growth of the remaining trees. We could use this to flux carbon to the other pools. And the idea here is that we're reducing competition for light and other resources. And we can use a variety of practices, right? So single tree selection, group selection, crop tree release is a great practice for this. Timber stand improvement, variable density thinning, et cetera. So there's a lot of different ways we consider this to improve the growth of the remaining trees. Some sources recommend removals of less than 25% of the basal area over 20 years. And that really comes from northern hardwood stands. So as we think about some of these practices and folks want actual numbers on the amount they should remove or leave, we do need to consider that varies by where you are, where your forest is, and by the forest type. So greater tree vigor we could increase the flux of carbon to the soil, right? So if we have healthier, more vigorous trees, we actually do get more root exudation. I mentioned this last week. That is one of the biggest ways we get carbon into the soil to be stored long term. And this is a great practice to promote resilience. This can be used to increase age and species diversity, the complexity of our stands. So trees could be felled and left in place or girdled to promote deadwood. It certainly reduces competition for light and resources, which are critical under a changing climate, and can lessen the impact from disturbances. Could result in a higher proportion of wood for durable wood products, but that is pretty uncertain, depends on your forest type, the practice, the quality of the trees. The important consideration here is this will reduce carbon stocks in the short term. When you're harvesting, you're removing carbon from the woods, and the goal here is promoting the sequestration of the remaining trees. Landowners will have to consider pre-commercial thinning, commercial thinning, what the economic returns are, cost markets. This is sort of a tough one right now, as we don't have a lot of markets for pulp and fuel wood. And so doing this kind of thinning can be, there might not be a lot of economic revenue that a landowner achieves in this practice. We do know that from work from New Hampshire that we can achieve thinning can achieve similar carbon stocks to no management. And this shows different types of thinning from below, thinning from the middle and above, compared to the control over 2 time steps. And importantly, this is, I think, a really critical component when we talk about forest management, is active management is known to decrease the rates of tree mortality. So this is showing unmanaged stands here, managed stands here, and regardless of where the stocking is, the above ground woody carbon stock, the actively managed stands have a lot less mortality through, a lot less carbon losses because of mortality. And that's because those, they've been thinned, those trees have been removed as wood products, and then those wood products are not, the carbon is not immediately emitted. It is stored for as long as those products are in use, and even longer if those products are then sent to landfill. Or often they're combusted and used for heat or energy, and we get additional benefits. We can also do things to increase the proportion of younger age classes in our woods. And again, this is sort of a long-term goal to increase sequestration and carbon storage of the newly regenerating trees. There are a number of different ways this can happen depending on forest type condition, right? Group selection, patch cuts using shelter wood systems. Generally, the recommendations are not to exceed more than 20% of the stand over a 20-year period. Generally, uneven age management will result in higher carbon stocks than even age, but this again is variable, and we're still learning more about this with continued research that is being generated. This is the idea to capitalize on the fast growth of young trees, right? You look at that sequestration chart over age development of a stand. Younger age classes are sequestering carbon at a higher rate. And so if this is done carefully, we can increase the stand-wide carbon sequestration rate by having some areas of young forest, some areas of mature forest. Importantly, this is a great strategy for advancing resilience. It allows for higher diversity of age classes. You have diversity in structure across your parcel. And it can really benefit some critical wildlife species, particularly migrating birds that rely on some of these early successional forest stands for nesting or fledging of young. If we pair this with other strategies that I've talked about, and we'll talk about with retention, keeping areas of reserves, right? Large trees, using crop tree release, we can sort of maximize both storage and sequestration on our parcel. There will be a temporary loss of carbon until those young trees have grown up. And critically in our region, we really need to consider how do we protect those young stems from browse and competition, for example, from beech sprouts, if an issue. And a lot of that is pairing the right size gap with the conditions. So we know that if we do larger gaps, we can sort of overwhelm the browse pressure. But this is really dependent on what your goals are on the forest parcel. We can also increase structural complexity using forest management. So this is the idea of increasing size and age class diversity across our stands. So I just mentioned one way to increase age class diversity is increasing regeneration. But we can also do this by including retention, large trees, keeping large trees on site, tip-ups, cavities, and other features, emulating natural disturbance regimes. We can do things like small group and single tree selection, structural complexity enhancement, which is Dr. Bill Keaton's forest management technique to sort of get some of these additional structural complexity components in our forest, and also thinking about carbon. We can use things like expanding gap or regular shelter wood systems, which are great to increase that structural complexity in our forests. So this is a strategy to maximize sequestration opportunity. Again, this is a really stellar strategy for increasing forest resilience, right? So we're just increasing sort of the messiness and the parts of the forest that might be missing in a lot of our forests because of land use, our land use history, and our young forests. It also associated with a lot of other ecological benefits, so biodiversity, old forest characteristics, etc. You will have an initial decline of carbon stocks. Again, anytime we're doing forest management, there will be a decline in carbon because some amount of carbon is being removed in harvested wood. Not all of that carbon will be immediately released. We could have a high influx of deadwood from this practice, and that's a great, most of our forests in New England, New York are lacking deadwood. They have less deadwood than they would have historically had before widespread land clearing. And so, but when we have deadwood, that wood is no longer, actively sequestering, it's slowly decomposing. So you can have a situation where you have some increased emissions because of this deadwood pool. And it's important to think about, there's different ways we can talk about structural complexity. There's vertical, so that's looking at the forest and thinking, are there different layers of trees, different strata in the forest? Do we have, overstory and understory and midstory components, but also the horizontal structure. And I touched on that in the last slide with doing things that increase regeneration, like patch cuts. That increases the horizontal structure where you could have a mature forest right next to a young forest next to a mature forest. And that diversity across our landscape is really critical from a resilience standpoint and from a carbon sequestration standpoint. So we do know from work, from research done, that things like canopy gappiness, so that's having gaps in our canopy, and then areas of closed canopy, a range in tree diameters, large deadwood, vertical cover, tip-up mounds, cavity trees, those are all associated with higher above ground carbon. And it does depend on, there's a lot of factors, depends on what species are there and what conditions you have. And we know this is true even in second growth forests, that structural complexity is related to higher above ground carbon stocks. And a lot of our forests, this is an example in the middle, that we don't have a lot of complexity. And this is really a strategy that probably most forests could use assistance with. Next, we have, we can retain big trees. This is really, really important. I mentioned this last week, is that large trees disproportionately contribute to forest carbon stocks. We know this, it's just based on physical nature, the volume that they fill, and every year they're adding on more carbon to all surfaces of their structure. We can do things like legacy tree retention, so marking these trees as a legacy, crop tree release again, so removing competition around these large trees to make them even bigger, or extending our cutting cycles, as I mentioned earlier. And importantly, these are source of future deadwood, and they're source of large deadwood, which is something we are lacking in our forests pretty universally. This is a strategy that aims to keep more carbon on site, so to reduce emissions. And importantly, large trees, which often are the oldest ones in the forest, not always, they are a source of locally adapted genetics. So they are a source of pollen, of seed. And so it's really good practice when we can to keep those trees on site if possible. Adds to structural complexity, as I mentioned, and certainly biodiversity. It could reduce the economic value of your harvest, really depends on the situation. And if trees are to be permanent legacy, permanent retention, it might be helpful to consider ways to mark them such. So if land transfers ownership, those trees are kept in perpetuity to live out their life and die. When we pair this with strategies to promote younger age classes, this is a great way to sort of balance that maximizing storage and maximizing sequestration potential. So we do know from work, this is out west, so you can see that you might not recognize a lot of these species don't grow here, but we do know that large trees really disproportionately contribute to stand carbon, and that sites with higher biomass generally have more large trees. Next strategy is that we can increase the deadwood pool. So this is keeping, snags, standing dead trees, creating snags through forest management. So that might mean girdling and leaving standing trees, and considering trees that could be future snags, right? So trees that are sort of on their way out that might not be really economically worth much, but will be source of future deadwood or down deadwood. And we can create more of this too by felling and leaving in place. Consider a range of size classes, sort of larger is better. And that's really just has to do with what we lack in our woods, but also the rate of decomposition. A larger piece of deadwood will take a longer time to decompose, so it'll provide longer benefits. Goals would be, keeping a range of species in deadwood classes and conditions, but that's dependent on the forest. Leave tops on site as a good practice as possible and as feasible based on your forest management. So this is a goal to increase carbon stocks on site, right? So you're fluxing carbon from the live tree pool to the deadwood pool and trying to accumulate carbon in the deadwood pool. Importantly, we know that deadwood provides so many functions to our forests. And as I said, generally, we have less deadwood than we would in pre-colonial, pre-cleared forests. We know that deadwood protects litter and soil pools, right? It may add carbon to them over time. It can increase the sequestration of the remaining trees because we're sort of removing some competition, maybe from girdling or felling and leaving. And this is a really good practice for resilience. Deadwood holds water on site for a very long time. It shades and protects soils and roots, traps duff when we have overland flow of water down a slope. We can actually use deadwood to physically block that water and slow it down and trap sort of leaves and debris. It does a great job cycling nutrients. So deadwood has all sorts of nutrients in it that slowly decompose, promotes biodiversity, and really it can be used as a great strategy here in these lower figures to protect the regenerating seedlings and saplings from deer browse. We need to consider that there will be initial declines of carbon in the stand if live trees are sort of cycled to this deadwood pool. And we could have a high influx of emissions. Deadwood is known to we add more deadwood, we actually increase the microbial community in the pool. So that can happen, and that's just a natural process that is still providing a ton of benefits for our forests. And of course, we have to think about forest management. It could make it difficult for access. So you want to consider the landowner needs there. We do know that older forests just have more deadwood across the larger ranges of sizes and decay classes. The next is we can increase stocking. So this is reforestation or afforestation. The difference here is usually reforestation is increasing stockings in places that are already forests, whereas afforestation is increasing stocking in places that are not forests, like an old field. So this increases forest carbon storage, of course, can provide lots of other benefits that trees and forests provide us, right? And community resilience. It's important that we consider that, our goal isn't just to get everything to the highest stocking possible. At high stocking, we have lots of vulnerabilities. So individual tree vigor can decline as trees are closer and closer together, and their sequestration can decline. We can actually have increases in mortality when stand stocking is too high. Carbon benefits of increasing stocking are slow to accrue. So we need to consider that is an important part of this. If we do planting versus natural regeneration, we have maintenance costs. We may consider use of future adapted species that are projected to do better under a changing climate. And of course, again, we need to manage for competition and browse, because without that, we could lose that increase in stocking. And so there's been some work in our region, so example here, well, actually this comes from Midwest, but tree density is strongly related to higher carbon storage, but lower sequestration. So again, this is what our balance is and what our goals are. And this map shows potential gains in our region if potential gains in carbon if poorly stocked and medium stocked acres in our region were fully occupied. And you may have all heard about sort of the Trillion Trees projects and these efforts to increase planting in areas. So this is an afforestation technique of increasing tree cover in places that currently do not have tree cover. And you can see this is a great resource, reforestationhub.org. You can play around with what it looks like for your area, but there are large potential gains in carbon if these unoccupied areas and low stocked forests were reforested. But again, for this, really important to consider trade-offs with land use. We can also increase species diversity. This is similar to the structural diversity, structural complexity strategy. It's really just occupying more niches in our forest. If we have more species, we can have higher carbon stocks. It's important to consider functional diversity when we think about species diversity. So it's not just a sugar maple versus a red maple, but thinking about trees with different strategies, life strategies. So conifers versus broadleaf trees, mid-tolerant versus highly tolerant species. And management actions will really depend on what target species you're thinking of increasing, what exists on site. This is a strategy to maximize and stabilize carbon stocks over time, right? So it's sort of a protection. If we have disturbance, when we have more climate change, if you have different species in the forest, a variety of species, you sort of have a better ability to continue as a forest in the future. This is a great strategy for forest resilience and, of course, other ecological benefits. Promoting more species promotes biodiversity as well. You'll have an initial decline of carbon stocks, like I've mentioned multiple times with active management. You may want to consider favoring future climate adapted species. So in general, those are species that are adapted to sort of warmer and drier conditions than in the future versus our sort of cold adapted species. And diversity, again, can be vertical or horizontal. So we don't need to think about this happening in every stand of the forest of our parcel, but across our parcel, across the landscape, thinking about what the adjacent forests are to land that you're managing or land that you own. We know that above ground carbon is related to composition and diversity. This comes from long-term study plots, forest inventory and analysis plots by the US Forest Service. And maximum above ground carbon is higher in stands with higher species diversity, which is important to know. Another strategy is planning to harvest and retain quality trees and also limit residual damage. So this is sort of a co-benefit strategy that you're sort of reducing emissions and increasing carbon sequestration of the remaining trees. So this is the idea that we're carefully planning harvests to reduce damage to the residual trees that remain on site. And damage to trees can reduce their carbon sequestration rate and storage if decay and rot are introduced. So this happens a lot here in this bottom figure when we get physical damage to trees. And over time, we can have fungi or bacteria, different pathogens entering those wounds and causing wood decay. And we do know a healthy, productive forests, right, are best for storage and sequestration. So this is really a long-term goal and to reduce the emissions from decay and mortality. The carbon gains are really minimal, but this is a great practice to think about for the longevity of a forest site and increasing returns in the future. A lot of people are interested in the impacts of salvage harvest on carbon. And this is sort of a hard one to really give a concrete answer to because it's quite varied. But we do know, as with any timber harvest, if we do pre or post disturbance salvage, that will reduce carbon stocks on site. If we can get a lot of those harvested materials into products that are storing carbon, not all of that carbon will be immediately released. Or if we can use those products to offset uses of other greenhouse gas intensive products, that's a great benefit as well. But we do know that it's really dependent on the stocking of the host species, the amount of salvage that is removed, and the previous management that happened on that site. So it's really important to consider carbon in harvested wood products, the value of the harvested wood products, as well as the other site goals, right? So forest health, regeneration, maybe salvage is an opportunity to increase species diversity in some other areas. So this is an example of some work done in some modeling done for spruce budworm. And what you'll see here, these are modeled, and what it shows is that salvage reduced carbon stocks compared to no salvage, but only for about a decade or two. But this is really dependent on host density and previous silviculture. So the previous silviculture is noted up here. So this is a commercial industrial harvest, heavy cut, moderate cut, high grading, light and no management. And across these numbers is a higher density of the host species, thus higher risk of spruce budworm damage and lower density risk. And all of these are compared to this benchmark, which is the reference. And you can see that there are differences between salvage and no salvage across these panels. When we look at no management, we can see that it does really depend on, if we have a high density stand, there is a difference in carbon, but about year 20 between the salvage and no salvage, they're the same, pretty indistinguishable. If we have a low density site, there's really not much difference between the salvage and no salvage sites. In a Minnesota study, they found that salvage after blowdown and fire reduced carbon stocks, except the down woody debris. So the dead wood on the ground had equal amounts of carbon. But this study didn't include carbon that was then transferred to harvested wood products. Another question that is common to hear, and it's just, it's great that folks are concerned about this, but how does harvesting affect soil carbon? What we know from a number of studies is that harvesting has the biggest effects on the litter and the organic layer of the soil. So that's sort of like the forest floor, the really rich, dark color layer of the forest floor, but that harvesting typically results in quite minor losses to the deeper soil layers, to the mineral soil carbon. But this really varies, and it actually varies more based on soil type, and moisture, sort of texture of the soil, slope, things like that have to do with the physical properties of the soil. One critical thing that we can do with the soil pool is think about our landings, our log landings, and our roads, because those often mix these soil layers by use of heavy equipment, building those and grading those. So mixes soil layers and residues and can be a really large source of emissions. So we know that from some work that has been done looking at these log landings, and importantly, this releases methane. And I touched on this a little bit last week. Methane is another greenhouse gas and quite important in our our climate change issue in the greenhouse effect. And we know that when we sort of compact soils and bury logs, we actually get anaerobic decomposition, which is decomposition without oxygen, produces methane. And so this is really critical to be aware of. And so limiting the size of these areas or doing other things to reduce the tilling of soils is critical. So we've seen that in research from the region, no statistical difference in soil carbon by management intensity. And you see that there's differences in the soil carbon, but they're non-significant differences. There's differences based on site characteristics. We do know that forest floor carbon losses occur, and this, regardless of conifer or mixed or hardwood forest types, we do see losses. But we do know that changes in forest floor carbon from harvesting varies quite significantly by soil type. And this is just showing some different soil types that we can have, and that is one of the key factors. So a strategy here is really protecting the soil and litter carbon pools. So this is keeping carbon where it is, reducing sources of emissions. Following acceptable management practices and best management practices that we all have for our states to protect soil and water, also protect soil carbon. So reducing soil compaction, as I mentioned, reducing rutting, tilling, impacts to the soil is critical. As I mentioned, the deadwood strategy, deadwood is really great to protect both soil and water and may help build soil carbon over the long term. We probably can't do much to increase soil carbon. It's just very slow to accrue. And it's really best to do what we can to protect. And of course, this is associated with many other ecological benefits we have, right? Like biodiversity, resilience of our water sources. So keeping, soil where it is, reduces the turbidity of water, reduces other impacts we have to our waterways. There's, of course, management trade-offs, right? We have, we might need to use scarification to promote regeneration of certain species like oak, like red oak or yellow birch. We need roads, right? And there might be costs associated with trying to limit this, but thinking about road layout is critical. Reusing roads or thinking about ways we can reduce our impacts on these surfaces, right? So using branches, bridges, whatever things, winter harvests to reduce impacts on soil are really important, but recognizing not all disturbances can be avoided. We do know that land use change and fire result in larger carbon losses from the soil than harvest, right? So the losses we have at harvest are much smaller than a lot of other impacts we have on the land. Another consideration here, and this is one to think about sort of in a broader sense, is increasing proportion of durable wood products. So this is seeking to harvest or produce, right, manufacture products that can be long-lived. So this is thinking about ways to be efficient, less waste in our products, or in using these products instead of other high greenhouse gas products. That's great. Anytime we can substitute wood for steel, concrete, it's a little bit harder, but plastics is a great way for us to keep carbon out of the atmosphere and have a lasting benefit. So this is avoiding emissions, increasing the forest sector carbon stock. So it's not increasing the amount of carbon in the woods, but increasing the amount of carbon that's kept out of the atmosphere. If products are used for longer than the equal amount of wood growth occurs, we can accrue carbon over time. And this is what's happening in many of our states. I don't know specifically, but I've looked at this for Vermont. We are accruing carbon in our stored wood products over time. And we have much more growth in our forests and harvest. So every year that amount goes up. And of course, this can be paired with other strategies I've mentioned to increase carbon on site. A lot of folks have been looking at, is it possible to accumulate benefits with multiple thinnings, multiple entries in our forest, and get more carbon than we would have had in that site if it had not been harvested. And it seems possible. It's a lot of unknowns. And you have to remember too, as I mentioned earlier in the webinar, areas without active management are likely going to have more losses from mortality. So how can we think about forest management to reduce mortality, reduce carbon losses, and increase carbon storage? Of course, it's not possible in all stands, and a landowner or forester might have little ability to dictate where products go, and certainly their efficiency. Difficult to quantify these outcomes across the supply chain. And when we talk about next week, carbon offset programs and payments, sometimes this is included, sometimes not, and it really gets down to, it's sort of hard to track and hard to quantify. The other one strategy that's sort of akin to this is thinking about our forest economy, our forest industry. Are there ways that we can reduce emissions from our forest supply chain, right? So there's many ways that we have technology to reduce emissions from other part of the supply chain, like biofuels, using electricity, better efficiency, promoting better recycling and reuse of wood products. And this is really critical because when we talk about forest carbon, what we're talking about is really need to reduce the amount of greenhouse gases in our atmosphere. That's the issue we have. And so we need to stop emitting greenhouse gases from the fossil fuel industry. Because as I talked about last week, and I showed that schematic of the global carbon budget, we're releasing carbon from the fossil fuel pool at a much, 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 much faster rate than it could ever go back into that pool. And so that is critical. And so are there ways when we think about forest carbon, we can think about reductions in our greenhouse gases across the industry? And this is really hard. This is going to be something that will take, no one person will be able to work on, but thinking about this as a community. And this could really help us be better positioned in the future too, right? So it's a resilience for our forest industry and forest sector. These are not, these sort of reductions are not included in carbon offset payments and programs yet. And so it sort of needs to catch up with the needs. And it will certainly require considerable incentives to help folks transition. We don't have, we don't have heavy equipment that is electrified at this point. So what can we do to reduce some of our emissions in the woods and in our production? Some folks some mills are using their waste wood to heat their facilities. This is a great way to sort of have this reuse of materials that would otherwise emit carbon as they decompose. All right, I wanted to introduce a few management guides to folks for more information. So this is a recently released publication by the Northern Institute of Applied Climate Science and the Nature Conservancy, and called Our Forests and Our Future. Now, a number of the strategies that I've mentioned here are talked about, sort of a general concepts are given in the beginning about why it's important to consider your forests with climate change in mind. The exemplary forestry in the Acadian Forest region is a great publication by the New England Forestry Foundation, not solely focused on carbon, but focused on sort of good ecological practices that really incorporate resilience in the future. And so therefore, carbon is sort of integral to that. And then the USDA Forest Service and NIACS have released this great, really, it's a lot of information here, but forest adaptation resources. There's analysis of climate change impacts to our forests here in the Northeast, menu of adaptation strategies and approaches. You can use an online workbook or paper workbook to work through a specific site you have, specific management plan, and consider climate change in that. And so this includes forest carbon management with concepts of climate resilience. Lots of folks, foresters have asked me about how do I measure carbon in the woods? And the thing is about carbon, and I think I stressed this last week, is it's very labor intensive and cost intensive to measure. And that's because it's quite variable through a forest, and we need to go out and actually quantify the biomass in trees, in parts of the forest we can't see, like soils, roots. Deadwood is particularly hard to measure because it's in various shapes and decay classes, so we have to make a lot of assumptions. Typically, carbon is measured in permanent fixed area plots with a lot of different measurements that are compiled to produce carbon estimates. But for most foresters that's not something that they have time to do. And most foresters are doing horizontal point sampling, so cruise plots. And there is a way that you can estimate carbon from those data points. And so it'll give you more of a ballpark of where the forest is in terms of carbon. And really you're focusing on sort of the tree pool, the live tree pool. You can also focus on the dead tree pool in doing that. So a couple examples that are come out from the Forest Service. This is Pearson management guidelines for the sequestration of forest carbon. And so the idea here is you can use your cruise data to calculate biomass directly from standing growing stock volume. And you can do this, they have factors developed for each forest region, so you can use these factors to multiply out. You could also calculate these expansion factors yourself based on your site characteristics. It's a little more intensive, but it's not too challenging. And they found that these give reasonable estimates of tree carbon. You can also, there's an example here, and I bring this up, show this because this is how we do point sampling on Vermont state lands. We use the big BAF sampling protocol. And so there's using 2 angle gauges or 2 different size prisms. And so you can do this, there's a good protocol for this, applications of big BAF sampling for estimating carbon in small woodlots. And really you use the 2 different angle gauges, one to count trees and estimate basal area, and then a different one for detailed measurements. And so again, these will provide sort of rough ballpark estimates if you want to understand where a parcel is in terms of forest carbon that can maybe help you consider management objectives. And as I mentioned last week, for sequestration, you'll need 2 points over time to look at the change in carbon storage. And as far as frequency, maybe 5 to 10 years, really depends on your goals, and the number of plots depends on the variability within your stand. But check out these resources for more information. And I will plug that on the Northeast Forest Carbon website, we are adding additional resources too. And a lot of these tools for estimating carbon, we have links and descriptions of them on the website. And so I organized these as sort of like easier to use, harder to use resources and tools you can look at. So these really give you a sense of how your land might compare, but these ones are not based on a lot of measurements you'll take in the woods. So we have a number of tools from the iTree suite of software, which are online, fairly easy to use for most people. And so, example of just putting in the carbon, generating the carbon estimates of a single tree, storage and sequestration rate, right? So here we have iTree design, allows you to put in some information about your parcel, and only a few requirements needed. The Nature Conservancy has a resilience land tool where you can put in a polygon or actually upload the shape file of the property you're looking at, and it will provide estimates of carbon stocks and potential future sequestration for that area. iTree Harvest is used to estimate carbon in harvested wood products. That it needs inputs on what volume was removed, the type of wood, where the harvest occurred. iTree Canopy uses aerial imagery to conduct a cover assessment for an area, and will give you carbon estimates and other ecosystem services. The most challenging, but the most accurate of all these is the Forest Vegetation Simulator. This is often what is used by folks that are really needing to model and estimate carbon stocks for things like carbon payment programs, which we'll talk about next week. This requires in-depth inventory from the woods that is inputted, and is a pretty it takes a little bit of work to get to know how to use this, but you can actually grow out your trees in the future under different management scenarios and look at the carbon differences that are projected. I mentioned the Reforestation Hub, which focuses on reforestation and afforestation, associated carbon gains, and then the Forest Inventory Analysis, Forest Service program has a course 40 degree dashboard, which shows the amount of carbon in deadwood across our region. That is a fun thing to play with. Cost benefits are an interesting thing to think about when we talk about forest management for carbon. So this shows here on the y-axis the estimated cost to implement these practices in dollars per acre, and on the x-axis is potential forest sequestration above the baseline. Where baseline is, if you didn't do this practice, how much additional carbon could you sequester? And again, this is acres per year, right? So sequestration is a rate that carbon is taken in. And these data come, I modified them slightly and removed some that weren't applicable, but this comes from the Maine Carbon Task Force final report. They've been doing a lot of work looking into this for the state of Maine. And what you'll see here is we have a range of potential forest sequestration benefits and potential costs, right? So here, the lowest, this is one of the strategies I mentioned, retain quality trees and minimize stand damage, right? Pretty, no cost to doing that. It's just avoiding those damages. The gains are pretty minimal, but because it's no cost, that's not a bad trade-off, right? Again, there's some other no cost benefits or practices here. Of course, passive management is one. Extend harvest cycles to grow larger trees. Not really a cost. There might be some lost opportunity costs, but there's no cost to do that. Or try and increase the proportion of long-lived products. And then you have some of these practices which do have higher costs to doing. And one, importantly, I stressed at the beginning, the avoid forest loss. You can see here that the axis is much further along, that we have such potential with avoiding forest loss to have great benefits. The cost here is really unknown. It really depends on how we're protecting that land from forest losses. And so that can range, as we all know in our region, that could range from, who knows, per acre, and what the circumstances are behind that potential forest loss. And as I mentioned earlier, forest conversion to another land use results in emissions of that stored carbon. So in addition to this potential forest sequestration above baseline, this is that foregone sequestration that you would get if you avoided forest loss, you also keep carbon on site. This has great benefits, but could have large costs. I think it's also really critical to talk about trade-offs to consider when we are managing for forest carbon. So we know that there's a trade-off between storage and sequestration and mitigation, taking in carbon versus resilience. But also critically, we know that there's a trade-off with wildlife habitats for species that need early successional habitat. There's certainly trade-off with revenue, and markets will demand what that revenue is, and certainly impacts here versus impacts away. And I love this quote by Paul Catanzaro and Tony D'Amato in their Forest Carbon, an Essential Natural Solution for Climate Change. Forests provide many essential benefits, including carbon, but not always in equal proportion. Choosing a strategy for your forest may mean that some benefits are enhanced while others are reduced. And we think about this too across scale, across the landscape, and having diversity of forest conditions over time and space really does provide the largest range of benefit, including carbon and resilience. And of course, we need to consider leakage when we're talking about forest carbon management. And that again is reductions in timber harvest could cause increased harvest elsewhere to meet demands. What we can do is try to maintain consistent and sustainable harvest volumes as a community until we can decrease wood consumption, increase wood recycling and reuse. But really, this is something we need to talk about as a community and will require a broad initiative. Critically, it's important to recognize in the US and in many of our states, we import more wood than we export. And when we talk about carbon, we sort of only think about that within a state boundary. So this is something that we need to consider of not pushing our impacts elsewhere. And essentially that negates any carbon benefits we would have had and probably has many more negative impacts. So summary, take home points, all management decisions or lack thereof affect forest carbon. Keeping forests as forests is the most important action we can take. It's also really critical when we're managing for forest carbon, we have to think about climate change and climate change resilience. We have many options for reducing carbon emissions and increasing carbon stocks that ideally are combined in a management plan across multiple scales, but consider balancing goals and trade-offs. And it's important that we evaluate outcomes. And this does require estimating forest stocks, which is really a challenging thing to do. Management can occur without or with selling the carbon. And I'll talk about this more next week of incentive programs and payment programs for forest carbon. So that will be next week, Wednesday, same time, May 18th, carbon markets and incentives. Thank you all for listening. I'll take some questions.
Wonderful presentation. Again, a reminder, it is recorded and it will be posted on the website, northeastforestcarbon.org, along with all these materials. So we do have some questions. We have some time, so we're going to go through them. But I want to start just by talking about the use of the chat. And I do this because several people sent private chats to me during the presentation complaining about the excessive chat that is distracting from the presentation. I can only ask you to be careful about using the chat and using it only for questions. We've got 2 more webinars and I'll ask you to do that there, and I'll leave it at that. And so here's some questions to start us. I don't think we're going to get to all of them. And as I said before, you can email me questions you really want answered after the fact, and we'll get answers to you. And this is Charlie Levesque, in case I didn't say that, you're not seeing me. So the first one, Ali, is really about invasive plants. And, just talk a little bit more about the effects of invasive plants and increasing invasive plants on, forest carbon, if you could.
Yeah, so yes, all of our states have invasive plants, and one of the biggest negative things that they're having in our forests is reducing biodiversity. And critically, when we talk about forests and carbon, resilient forest carbon, they're going to be competition for tree seedlings to grow, germinate, seeds to germinate and grow up and have space and room and resources to grow. So we've seen this in a lot of places where have really dense cover of invasive species. There might be no seedlings, tree seedlings in that understory. And so that's a critical component to thinking about the longevity of our forests, is managing or trying to control those invasive species so that we can allow for some regeneration to happen. And then we see this too with not only invasive species, but species like American beech that is suffering from beech bark disease and sprouting, right? A lot of us maybe have heard the term beech hell in our region, where we see only beech sprouts coming up. Again, those are going to be competition to other types of trees growing up. And so to increase resilience, we really want to think about making sure we have a future forest and we have as much species diversity as we can.
Super. So one of your slides early on was sort of outlined the amount of wood that is entering landfills from various harvesting techniques. And the question is, how do we know more clear-cut harvest wood ends up in a landfill as compared to other harvest methods? And maybe the graph was not read correctly. It's if you want to go back to it, if you know what I'm talking about, maybe be helpful to look at, but it at least.
Oh yeah, okay, so I know what you're talking about. Yes, so so a lot of that, it's based on modeling of where I say we, but where folks have modeled that wood products go, and so that happens to be just based on. Right, so clear cutting is generally happens in certain forest types. It's a even age management technique, so it's more often to occur in conifer stands, and so likely that those maybe went more into paper products or other products that have a shorter carbon storage in use, but then go to landfill. I wish I had it up here, but in the talk I gave last week, I showed some figures at the end of those curves by product type, so showing carbon storage in use when those products are in use versus in landfill. And there's really a difference based on the product and also the, are they hardwoods or softwoods? There were some differences there, sort of some surprising differences actually, but when you look at that. So yeah, so you're referring to the Nunnery and Keaton work looking at, oh, that was actually beech birch forest. So there was modeled clear cuts in those stands. And so they used, I believe, Forest Vegetation Simulator, which I mentioned as a tool, input inventory data. And that tool has models built in based on where, the quality of the tree, the size, and what silvicultural strategy you would do. So I'd have to look into some of the details if anybody here has input on that. But it's really based on where we have sort of model generally where different products go. And so that one was the difference between two clear cut, a 15-year clear cut, a 30-year clear cut, I think, for return. So it's probably based on where the product that was harvested from that forest and what type of product it was. I'd have to look into that a little bit more.
Okay, thanks. You talked several times early on about leaving standing large trees and also talked about deadwood. And the question is, do you have a recommended basal area of acceptable cull that will complement long-term timber management, obviously in the context of forest carbon?
For creating deadwood?
Yeah, how much should we leave?
Oh boy, yeah. It's sort of dependent on, any amount you can do. I've seen some recommendations, like a handful of, leaving a handful of standing dead trees per acre, like 4 something like that snags per acre. Felling and leaving is really dependent on what exists already. Is there deadwood in the woods already? I'd have to provide you some actual estimates. I can get those and send them to you, Charlie.
Okay, great. We'll do that. So talking further about deadwood and in answering this question, obviously you're going to talk about deadwood on the surface of the forest soil versus what might be under, but does the decomposition of deadwood into methane outweigh the benefit of leaving it, since methane is so much more problematic from a atmospheric greenhouse gas perspective?
Well, methane is really being produced when we have anaerobic conditions. So it actually can happen really in supernatural, in natural circumstances. So example is a floodplain forest, a forest that has saturated wet soils, may have anaerobic conditions. Wetlands have anaerobic conditions. So that does happen. And you think about a wetland, actually, those anaerobic conditions can often lead to a buildup of the organic material that doesn't decompose as fast. Certainly, if our actions are causing more methane, so things like I talked about landings and roads where we unintentionally sort of mix and bury wood products, wood materials, so slash and residues from harvesting. That's where we see sort of increases in methane compared to a baseline, which would be without those impacts. And so that's where we can have the biggest change. But as far as root systems underground, those will decompose. And if we aren't impacting the sort of decomposition from aerobic to anaerobic, that shouldn't be too big of an effect.
Well, here's a very detailed one. I don't know if you'll be able to answer, but can you comment on the importance of leaf area index in eastern forests and how certain strategies maximizing leaf area index could be used to better offset very high soil respiration in young forests?
So we know that leaf area index, which is basically like the area of a tree's leaves over if you took all those leaves off and like laid them down on the ground. And it's usually quite large. If you think about, especially an open grown, really mature, large tree, it has a huge area of leaves. And so we do know that that's directly related to carbon sequestration, which makes sense because the area that, the place that carbon sequestration happens in a tree is where there's photosynthesis, and that happens in leaves. So more leaves, more area generally means higher rates of sequestration. So then you're going to get more storage. So things like crop tree release, right? So growing bigger, larger trees, reducing the density of your stand can mean that you have bigger trees, you have fuller crowns. And crop tree release is this idea that we sort of remove other trees whose crowns are touching or encroaching the tree we're trying to keep. And we can do that on one side, two sides, three, four sides. Obviously, four sides would release the crown and give it the most space to grow. As far as offsetting the soil respiration rates, I don't know that I can comment on that in a way that's, I don't have the data on that exactly, but it might be something we can look up.
All right, thanks. Well, we have time for a few more questions. You talked a little bit about various uses of wood that is harvested, and some of those uses being long-term uses of wood. But this is a question about using wood for energy. What is the effect of using wood resources for heat and power generation, since this is carbon neutral over the long term? So in the bigger picture of things, using wood for energy, how does that affect?
Yeah, it's a great question, and one that's certainly relevant to our region and our states. So one thing we do know is that using wood for energy is actually not as efficient as some fossil fuels. It's just because they're not as carbon dense. There's water in them and other, other components to wood. It's not as pure carbon as those other fossil fuels. But really using it for heat, I think is considered a more efficient. And so doing the combined heat and power. This is a little bit getting out of my expertise, but I have been working on this a little bit in Vermont and thinking about this and talking to folks. And so that is considered a much more efficient use of wood, the combined heat and power generation. And certainly this idea of carbon neutrality is hard because as we see when we remove wood from a forest, right, we're removing that carbon. Some of the carbon is going to be immediately released in that management just because we have slash and we are increasing decomposition rates, or we have an impact to the soil because of our log landing or our roads, right? So there are some carbon emissions that will sort of be unavoidable. But again, if we do that in a sustainable and thoughtful way, it allows the remaining trees potentially increase their sequestration, increase their resilience in the long term, all those other benefits I mentioned that over time, so it probably will take, depends on the forest type, it depends on the amount of product you've removed in that harvest, but it will take a few decades to recover those carbon losses. And critically important too is, are we using that wood energy and heat to offset uses of fossil fuels? Again, that's, our dependence on the fossil fuel is one thing we really need to wean off. Our states have lots of wood. Is there an opportunity here to continue to use wood, especially considering that we have quite a lot of pulp and fuel wood in our woods that don't have a lot of other markets right now. And to do some of this management, we need to make it economically viable for landowners. And part of that is having some other ways we can use some of the products in our woods and help us with our thinning practices, right? Or if we're doing some regeneration cuts, there's going to be quite a lot of wood that's not going to go into these long-term durable wood products. So can we use some of that into heat and energy? So it's a great question, and one that's certainly very actively debated right now.
And aside from the science on that, just for everybody, the federal government through EPA regulations, as well as the European Union, have both declared wood energy to be carbon neutral. So maybe not totally scientific, but that's political decisions that have been made. One more question. There are many more that we're not getting to, and a reminder to send me the questions you want answered if we didn't get to it via email. But this one is there a soil color guide for estimating soil carbon?
I don't
Is
think.
there an easy way to estimate, I guess?
So I'm involved with a project, well, on a stakeholder group that's being run by Luke Nave, who works for the Northern Institute of Applied Climate Science in the U.S. Forest Service. He's a soil scientist, and he is working on sort of wall-to-wall maps in our region that predict soil carbon, and it is really based on soil type. So he can then use soil type maps that, I think there's things of texture, maybe moisture content or sort of hydrology that are involved, and look at the soil carbon and potential impacts from management, because it really does depend what soil type you have on your land, what the impacts could be, losses from management, no losses, or even he's seen in some soil types there are gains actually in soil carbon because of fluxes to the carbon pool. So that will be not probably completed for another 2 years, but that will be a super helpful resource to all of us in this region. As far as looking at soil carbon now, I believe the TNC Resilient Lands tool does include soil carbon. It's modeled from permanent plots, and it's sort of one snapshot in time, but you can look at the soil carbon in your, if you want to upload a shape file of your parcel, you can explore that.
Great, thank you, Allie. I think we're going to close here, and if you could stop sharing your screen, I got a few closing remarks. And again, thank you so much for another wonderful presentation. We encourage everybody to register for next Wednesdays as well. So as I mentioned, if you're a forester, you will get an SAF CFE certificate directly via email if you stayed on for the entire webinar. You don't need to ask for one. That will be coming in the next week. I mentioned that recording of this and all the webinars are on the website, northeastforestcarbon.org. That's where everything is. As the PowerPoints will also be on available for you to review. I mentioned that you can email questions that didn't get answered, because we didn't answer all of them certainly, and we'll do our best to get them answered. And remember, you've got a state lead person in the Securing Northeast Forest Carbon program. That's all on the website, and you can contact that person, and you certainly can contact me about anything. And everything, again, is on the website, www.northeastforestcarbon.org, and we will see you next week.